So in Chapter 3, we're going to talk about energy. The Chapter 3 outline is going to include work, power, energy, potential energy, kinetic energy. Then we'll talk about forms of energy, energy conversion, and energy conservation, petroleum, oil, moving water, nuclear, and solar energy. So to start off with, we're going to talk about work. So we just finished talking about force in the last chapter, and now we're going to move into talking about work, which is going to be the product, meaning multiplied, of the applied force, and that force as it's applied to a distance that it's parallel to. And so some images of what this might look like is there's a box, the person is applying the force, and the box is moving a certain distance to the right. So there's a requirement that's really important. The object must move. So if you're applying a force, like this person right here, to a wall, the wall is obviously not going to move. So the distance of the object is 0 because it's not moving to the left, despite the force being applied. So in this case, even though the person is applying a certain amount of force, but the object is not moving, when we take force times distance and we set this equal to 0, the amount of work is going to be equal to 0. So even though you are exerting effort to push on the wall, you are not actually doing any work. The second thing is that the movement must be in the direction of the force. So in this image down here in the bottom, when the man picked up the box from the ground, the force was in the upward direction and the movement was also in the upward direction. But when the man started walking to the right with the box, the force is still being applied in the upward direction. He's holding the box up from the ground. However, the box is now moving to the right, and they are no longer parallel to each other down here. They are now what we call perpendicular. Therefore, even though he is exerting effort to carry the box, he is not doing any work. Okay, so both of these images show how requirements must be met in order to classify as work. So units of work. Well, if the formula is work equals force times distance, that's what the definition told us, there are going to be two different types of units, metric units and English units. Remember, we have our two different measurement systems. So in the last chapter, we learned that force is typically given units of newtons. Distance, if you remember back to our fundamental units, are usually in meters. So when we multiply the two, we're going to get what's called a Newton meter. Newton times meter. But that is often changed to units of joules, like pronounced like the royal joules. The abbreviation for joules is capital J, and joules really should make us think of energy. Anytime we hear the term joule, it's going to have something to do with energy. Now the English system units are going to be a little bit different. The force units in the English system are pounds, and instead of measuring things in meters, we measure them in feet. And so the unit is going to be pounds times foot, or what's called foot dash pounds, or abbreviated FT times LB. So this brings us to power. Power is going to be the rate, so this is thinking about how fast at which energy is transformed, or it's the rate of work. So sometimes when we think about power, you might think horsepower. So a really fast car will have a very high horsepower number versus a very slow car, maybe not as fast car, is going to have a lower horsepower number. Another way to think about power is climbing stairs or bleachers. You know that if you are to walk upstairs, and if you think about the stairs going up, the one thing that's consistent is that whether you walk or run upstairs, you're going to cover the same distance. You're going to cover the same elevation. But if you're walking upstairs, you're going very slow. Therefore, you're not expending a lot of power because you're going at a very slow rate. However, if you run upstairs very quickly, the rate is much faster. Therefore, you're going to exert more power to run upstairs than to walk. But the one thing that's the same is you're still exerting the same amount of work. So it doesn't matter the value of work when all things are held constant. Work is the same whether you run or walk. The thing that changes is how quickly, the amount of time that you are expending. Now, traditionally, the idea of power came from horsepower. You knew it took a certain number of horses to carry a wagon. And now we have an equivalent that 1 horsepower is going to equal a certain amount of watts. And so we have a system of units we can convert between because we don't normally use horses to do a whole lot in our lives anymore. So the units are going to be watts or horsepower. And the formula for power is capital P is equal to work divided by time. So in this case, say that I expend 100 joules walking up the stairs, and it takes me 1 minute to walk up the stairs. So the amount of power that I'm going to expend is 100 watts. Now if I run, now I'm going to run, and let's say I can run the stairs in half a minute, in 30 seconds. Well, this is going to be 200 watts of energy, so I'm expending more power to run up the stairs than to walk, but the amount of work done between the two situations is the same. Okay, so make sure you understand the difference between power and work. We sometimes use them interchangeably in our everyday language, but when it comes to physics, they do have different distinctions. So what is energy? Well, energy is the ability to do work, and we have multiple ways to classify. So if all of our energy comes from the sun, I think that's probably the one thing we can agree on in science. Energy can be fed into what's called potential energy or kinetic energy, and we're going to talk about how these two things are different. So potential energy, or PE, is energy that an object has because of its position, so where it's located. The formula is PE equals the mass times gravity times its height, so how far off of the ground it is. The higher up off the ground it is, the more potential energy. So potential energy is like the ball on the top of the hill. It has all the potential in the world to roll down the hill. This is a balloon that's full of air, and the person is holding it with their fingers. I know that's not really like a finger, but that's not tied off. The balloon is being held, pinched shut, and the potential is when the person releases the balloon, it's going to fly away. Same thing with this slingshot. He has the rock pulled all the way back, and that's potential energy that when it's released, it's going to undergo motion. So what this brings us to is kinetic energy. Kinetic energy, or KE, is the energy associated with motion. So that's a requirement. The object must be in motion. If you have a car that's sitting idle at a stop sign, waiting for the light to change to green, that's potential energy. It's only once the car begins to move, when the light turns green, that the car is undergoing kinetic energy. Even though the car is running, it's not kinetic energy, it's potential energy. So kinetic energy would be when the ball goes down the hill, or when the balloon is released and the air goes out one way and the balloon travels the other way. The formula for kinetic energy is KE equals 1/2 the mass times the velocity squared. So velocity is really the same as speed. Remember we talked about that in chapter 2? So it's how fast something is traveling. We see that the heavier an object travels, normally its velocity might be a lot lower, versus a smaller object is going to be able to travel a lot faster. Remember, those all go back to those force concepts we talked about in chapter 2. So there are 5 really main types of energy forms, and we classify them the following way. Mechanical, which is moving car, leaping frog, so motion, work, movement. We have chemical, which is going to be our food that we eat when it's digesting, striking a match. We have radiant, which in this diagram is going to be broken up into that should say thermal and electromagnetic. They're all going to be under the same umbrella, but we can further break them down. So thermal would be melting ice cream, heating soup. Electromagnetic is going to be the electromagnetic spectrum, so visible light, infrared radiation, radio waves, x-rays. Those all fall into the radiation category. Then we're going to have electrical, so lightning, power lines. And then we have nuclear, which is the fusion that we see in the sun and the stars, and the fission that's occurring inside of Earth's core. So those are all our different forms of energy. Now, energy can be converted between potential and kinetic energy, and it can go back and forth. So if we think about the ball at the top of the hill, when that person released the ball and it started traveling down the hill, all the energy that was stored as potential converted to kinetic energy as the ball moved down the hill. Now, and this can go vice versa. As the ball comes down the hill and then comes to a rest, all the kinetic energy is gone at that point. So a pendulum is a really great example because once you pull back the ball on the pendulum, it should theoretically, in the absence of friction, it should continue to swing back and forth for all of time. And that's because, as we see here, we have maximum potential energy at the top of each swing. And this could apply to you swinging back and forth on an actual swing. The maximum kinetic energy is here at the bottom. So as the pendulum swings up to the right, the kinetic energy is decreasing, and the potential energy is increasing. Now when we swing back down, the opposite happens. Now the kinetic energy is going to increase and the potential energy is going to decrease. But theoretically, they're increasing and decreasing at the same rate. Therefore, the overall value remains constant. And then, in theory, the pendulum should continue to do the pendulum thing for all of time. Energy conservation feeds really nicely into what we just discussed, which is that energy can be transferred, it can be converted between forms of energy, but energy is always going to be conserved. And this is a law. So another law, the law of conservation of energy, which tells us that energy can never be created or destroyed, so it must come from something, like the sun. Energy can be converted from one form, one of those 5 forms, to something else, but the total energy of the system, the universe, will always remain constant. So it's just like every other conservation law that we've seen thus far in saying that the total amount overall remain constant, even though it may look different, it may do different types of work, but it is always going to be held constant. So now we're going to take a break and then come back and talk about energy sources today and finish up chapter 3.